All right, Algebra 2, we're going to do part 2 of 8.3, still dealing with that number that we learned about yesterday, e, which is approximately 2.7182 ... We're going to do some graphing today. We're still working with exponential functions. Remember, an exponential function just means that your variable is the exponent. So remember, e is a number. It's not a variable. But here we have an exponent that's a variable x. So that makes that an exponential function. So I'm going to start by creating a table of values. Remember, f of x is the same thing as y. So I'm just going to put x and y. And I'm going to pick numbers -2, -1, 0, 1, and 2. And so I'm going to have e to the -2, e to the -1, e to the 0, e to the 1, and e to the 2. And then here's where we're going to need a calculator because we need to figure out what those values are so we can graph them. And I'm going to go ahead and put the inequality sign. So I'm going to start off with e to the -2. And I'm just going to round it to the nearest thousandths place. That's what we were practicing yesterday. So I am getting 0.135 for the first value. For the second value, I'm getting 0.368. Now this next one you really shouldn't need a calculator for, because remember we learned with the properties of exponents, if you raise something to the 0 power, what does it equal? It equals 1, which also means I get to use an equal sign and not an approximate sign because I'm not rounding anything. So it equals 1. Then e to the first power is approximately 2.718. And then e to the second power is approximately 7.389. So let's plot these points. Don't forget to label your x-axis and your y-axis. So I have -2, 0.135, so it's just a little bit above the x-axis. Then I have -1, 0.368, so it's not quite halfway up in between the 0 and the 1. Then we have 0, 1, 1, 2.718, so it's almost up to the 3, not quite. And then we have 2, 7.389, so it's above 7, not quite halfway to 8. Now remember when we graphed these before, we're getting the same shape. Remember, it's going to get close to something. In our case, it's getting close to the x-axis. It's not touching it, but it is very close to it. So let's talk about these three things: domain, range, and asymptote. Let's start with the asymptote. Remember we said if there's a number back here, that's going to tell you what your asymptote is. But this is like having a +0 because there's nothing back there. So that's why we're saying that it is going to get close to y equals 0. That's going to be our asymptote. That would be a horizontal line, and we're saying that that's what it's going to get close to. Now let's talk about range, because your range totally depends on where your asymptote is. Are we above or below the asymptote? Well, we are above it. So we would say that y is greater than 0 because everything comes above this asymptote. Now you see as I'm drawing it, I'm kind of drawing it a little bit below the x-axis, and it's not really below the x-axis, it's just I want to make sure we can see it, and it's hard to see a dotted line when you already have a solid line there. All right, domain. Remember, domain means, are there any restrictions for the x's? Well, we were able to plug in negatives, 0, positives. It's going to the left forever. And as it goes up, it's also going to the right forever. So there are no restrictions. We learned that for all exponential functions, our domain is all real numbers. So there we have our domain, our range, and our asymptote. All right, let's take a look at number 2. Now right away, I see that there's a number back here. That's going to already tell me what the asymptote is. Our asymptote is going to be y equals -2. So I'm going to go ahead and put that in my graph. All right. While I'm doing that, I'm going to go ahead and label both of my axes. And now I need table of values. I'm going to stick with the same numbers that we were working with in the last problem. And really, you can just plug this into the calculator just like you see it. So I'm going to show you what that would look like. So I would have 3 times e to the 0.5 times -2 power. And then behind it, I'm going to have -2. And so I would round that to -0.896. All right, well, I'm going to do the same thing for -1. If I plug that into the calculator, I'm going to get -0.180. If I plug a 0 in, I end up with exactly a 1. If I plug in a 1, I get 2.946. And if I plug in a 2, I get 6.155. So let's plot and see what our graph looks like. So we have -2, comma, -0.896. So it's not quite to the -1. Then we have -1, comma, -0.180. So it's really close to the x-axis. Then we have 0, 1, 1, 2.946. So almost all the way up to 3. And then we have 2, 6.155, so a little bit higher than the 6. So we're going to see a graph that gets close to the asymptote and then curves and continues to go up. Again, domain is going to be all real numbers. There are no restrictions to it. For the range, we're going to ask ourselves, is our graph above or below the asymptote? And it's above it, so we're going to say y is greater than -2 because our graph is all above the asymptote. All right, so example 3. Again, I'm going to look first and see if I can figure out the asymptote. That's based on this number back here. So the asymptote is y equals 4. So I'm going to go ahead and plot that in my picture. We'll go ahead and label excuse me, my axes. I'm going to do something different this time for the numbers that I'm going to plug in. I'm not going to do the same numbers that I always do. When we dealt with exponential functions earlier in the chapter, I told you guys that if this is not just an x, so in the last 2 problems it was just an exponent of an x, but here we have an x plus 2. I'm going to take x plus 2, set it equal to 0, subtract 2 from each side, and I'm going to get a -2. That is going to be my middle number. So now I need a couple of numbers smaller than -2, and then I want a couple of numbers that are bigger than -2. And that's how I'm going to determine what numbers I'm going to plug into my table of values. So again, with the first 2 examples, the exponent was just a plain x. That's why I used the normal numbers of -2 to +2. But here it's not just an x. So we set it equal to 0. We solved for x, and that told us what our middle number was going to be. Okay, so now I'm plugging numbers in. I'm going to put them into the calculator. So the first one, I'm going to get 4.203. When we plug in a -3, we're going to get 4.552. When we plug in a -2, we're going to get 5.5 exactly. When we plug in a -1, I would get 8.077. And when I plug in a 0, I'm going to get 15.084. So let's plot our points. So we're going to go -4, 4.203. So just a little bit above the asymptote. Then we have -3, 4.552, so halfway there to 5. Then we have -2, 5.5, -1, 8.077, and then we have 0, 15.084, which would be much further up here, so I'm not going to graph that particular point. So we see that we're close to the asymptote, and then we curve up and we go up very quickly. So we already know our asymptote is y equals 4. Because our graph is above that, we're going to say y is greater than 4. And again, this is an exponential function, and so our domain is all real numbers because there are no restrictions. All right, yesterday we reviewed the compound interest formula that we had learned prior to spring break. Today we have another formula to talk about. It's called the continuous compound interest. Here's the difference. So compound interest is when your interest is being compounded annually, which could mean that n is 1, or semi-annually would mean n is 2, or quarterly, or monthly, or daily, or any of those words. Continuous compound interest means that your money is constantly being compounded. It never stops being compounded. Every moment in time it's being compounded. And so we have a different formula. Now the way that I remember it is I just remember the word PERT. But this is capital P, which again stands for your principal, times E, remember that's the number we learned about yesterday, raised to the RT power. R is still your rate, but you're going to change it into a decimal, and T is your time. So this formula is actually easier than the other formula, which is why I really like it. So continuous compound interest, we're going to use PERT. So let's get started with it. So for this first example, it says you deposit $1,500 in an account that pays 12% annual interest compounded continuously. That's the key phrase right there. That lets you know that you're going to use that PERT formula. It says, what is the balance after 1 year? Okay, so $1,500 is the amount of money that we're investing. So that's our principal. 12% is the rate, but remember you have to change it to a decimal, so it's going to turn into 0.12, and then 1 year means that T is 1. So here we go, I'm just writing the formula down, PERT. So the amount of money that we're going to have, here we go, I'm going to plug in $1,500 for the P, then E, remember that's just a number, we're going to raise it to the 0.12 times 1 power. So here we are, we're going to plug it in. So I have 1,500 times E raised to the 0.12 times 1 power. Now remember that the answer that we get is based on money. So think about money. How many digits would you want behind the decimal point? You would want 2 because you would round it to the nearest cent. So we have to look at the third digit to determine if we round it up or keep it the same. Our third digit is a 5, so it's going to round that 4 up to a 5. So for our answer, we're going to say that after 1 year, we would have $1,691.25. All right, let's try the next one. Sally deposits $2,800 in an account that pays 7.5% annual interest compounded continuously. What is the balance after 2 years? All right, so the principal, how much is being invested? That's $2,800. The rate, 7.5%, but we have to change it into a decimal. So we're going to move our decimal point over 2 places. That means we're going to change it to 0.075. Remember, just because it has a decimal point doesn't make it a decimal. If you see the percent sign with it, you still have to change it from a percent into a decimal. And then our time is 2 years. So we're going to have P times E raised to the 0.075 times 2 power. Now here's where I'm going to caution you, and I should have said this on the last problem too. Depending on how your calculator is being used. So like right now my calculator is in math print. So when I plug it in, the way that I type it in is exactly how it looks on my paper. Hopefully, can you see that? It looks like it is on my paper. What I want to show you is, suppose that your calculator is not in math print, as a lot of calculators don't have math print. So 2800 times E. Now notice that this particular calculator, when it raises it, it automatically puts in a parentheses. But not all calculators do that. So if your calculator does not put a parentheses, you need to go ahead and open up a parentheses and then 0.075 times 2 and close your parentheses. If you don't have the parentheses around it and all you have is E raised to the 0.75 times 2, the calculator is going to do the order of operations and it's going to raise it to the 0.075 power, and then it's going to take that answer and multiply it by 2, and that's not what you want. So just be careful with how you plug it into the calculator. Again, we want to round it to the nearest cent. So this is going to be $3,253.14 because the third digit was a 5, and we're going to round that 3 up to a 4. All right, so last example. A radioactive substance decays in such a way that the amount of mass remaining after t days is given by the function m of t equals 13e to the negative 0.015t, where m of t is measured in kilograms. So I know word problems aren't everybody's favorite, but let me break this down for you. The m stands for mass because that's what this problem is talking about. So that's why they named it m. And they called it m of t because this function depends on how many days, and t represents the days. Okay, that's all that means. And they're letting you know that your units are going to be in kilograms. So letter A says find the mass when t is 0. So I'm going to be plugging in a 0 for the t. So I have 13 times e to the negative 0.015 times 0. Again, I'm plugging in a 0 in place of the t. And I'm going to plug it into the calculator just like what I have on my paper. And I'm going to get 13. No rounding necessary. It came out to exactly 13. So I'm going to use an equal sign. And I need to include units. And remember, they already told us kilograms. So that means at the beginning of this problem, before days were going by, it was 13 kilograms. All right, letter B, how much of the mass remains after 20 days? Well, all we're going to do is plug in a 20. So again, I have 13 times e to the negative 0.015 times 20. Again, I'm just going to plug that in exactly like I see it. Now this one we are going to have to round because it didn't come out exact, so I'm going to use an approximate symbol. And let's just keep on with the 3 digits behind the decimal point. So I'm going to have 9.631. Again, we need kilograms. So remember, this particular problem said that your substance is decaying. So it makes sense that it started at 13, and now as time has gone by, 20 days have gone by, what's left is less than what you started with. That makes perfect sense because this object is decaying. So lastly, it says how much of the mass remains after 45 days. So we are doing the same thing, except now we are plugging in a 45. So I'm writing the same formula we have been working with so far, plugging in a 45. We're going to have to round this one too. It's going to come out to an answer that is not exact. And so we're going to say that this is 6.619. Again, don't forget your units, kilograms. So as time is continuing to increase, we see that our object is indeed decaying. It's getting smaller because the mass is getting smaller. All right, so I believe the homework assignment for y'all is in the book. And again, tomorrow we will have a Zoom session at 8:15. So I look forward to seeing everybody's face tomorrow morning.